We are live from downtown Mill Bay. Yo.
Which one is this? The thing?
You have more than one?
Is it this?
No, that's old. That's ancient. This is the one that looks like
Solutions?
that one.
Yeah, we do that. Didn't we already do that? This, right?
Yeah, did we finish it?
No. Oh my god, took out my phone. We didn't finish it. We did it with the periodic table. Yeah, like, yeah.
Okay. Does everybody have this handout? Good. And I believe we were up to, if I my quick check at the beginning,
Yeah.
with Jillian, we were up to there with dipole forces. Yo. We may have, yeah. Go ahead. It's more about finding it. Because I always prove extra, but then people lose theirs, and then they slowly get taken away. Physics 10. Oh, here's some. No, I got another one here. You want another one?
Thanks.
Anybody else need a copy? Excellent. Sounds like we're ready to go, and the bell has rung. Spring has sprung, the grass has riz. I wonder where the flowers is. There should be one right at the top there. Looks like this. So, before the test, what we were doing was molecular polarity of compounds and how a compound, if it has asymmetry and two things that have a very different electronegativity, will have a positive end and a negative end. Luke? Bogus?
Is it this one?
It's part 2.
Oh, that sign's 10, bro.
Yeah, I got you.
It is the one that looks like this. It says solutions on the top. Let's go, 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 go. Permanent dipole. We drew a few of those on the board as far as I recall, and you had to do these ones. We ended up finding out most of those were symmetrical, but all of them show that if you have a compound with a different electronegativity and you can cut it, gentlemen, if you can cut it in a way that separates the charge, you will have a positive end and a negative end. This separation of charge is known as a dipole. And if it's in a whole molecule, it's a molecular dipole. You can have a dipole bond, so these are dipole bonds. Now, if you have CF, which I'm going to draw incorrectly, but it still shows the relationship. It's in 3 dimensions, but this is the same kind of relationship in 2. This is a dipole bond. So all of these will be negative, but if I slice it in half, there is no side that's positive and with the other side being negative. It has symmetry. No matter how I slice it, I can't get a positive and negative. Symmetrical. So this is non-polar. Whereas this one is polar. Just as a review from last day, we were also looking up the actual structures with that. And now we're going to talk about these dipole forces and how they interact. I left a lot of room here. Dipole forces. First of all, break apart the word. Dipole means 2 poles, like a north end and a south end, in this case a positive and negative. A bond. A So a dipole has two poles, a bond with a slightly positive and negative end. We require molecules with molecular polarity, which means not just the bond, it has to be asymmetrical. And it has to have a polar bond. If you have both of those things, you will have molecular polarity. It'll have a positive and a negative end.
But we can still refer to things as dipole even if they're not polar.
You can refer to the dipole bond,
Oh,
but you can't refer to the whole molecule as that. Because the whole molecule, because of its symmetry, is no longer has a dipole. Yeah. And the word dipole is used to refer to both, so it does get confusing sometimes, which is why I'm trying to be careful. The example I'm going to use is a covalent compound that has a very strong dipole, hydrogen chloride. Let's make that bigger. Hydrogen chloride gas has a greenish tinge, so I'll use green. And I'm going to really exaggerate the bonding to discuss some of the things in it. Now, does this bond have a dipole? It does. They have different electronegativities. Which one's more electronegative than the other? Chlorine is more electronegative. So we would say that chlorine is the slightly negative end, and hydrogen is the slightly positive end. Have I used this symbol before?
Yeah.
Okay. Nuke.
When deferring negative from positive ends, does it just come down to electronegativity?
Just electronegativity. And in terms of symmetry, I'm going to erase this. Well, no, it's asymmetrical. We can clearly divide it right through a center and have a positive and negative side. So we have, no, now I'm going to run out of room. I'm going to cheat. So that is the positive end of the dipole. That is the negative end of the dipole. And I'm going to show you another symbol. And sometimes we want to show the dipole in the actual bond. We will draw a little plus, and then we'll take an arrow and go like this. That means that's the positive end, and that's the negative end. So if you see an arrow like that on a bond, they're telling you which end's positive and which end's negative. Now, they're not full positive and negatives. It's not +1, -1. It's just that chlorine is a greedy sharer. Electrons hang out with chlorine a little bit more. Chlorine's more electronegative. It's more attractive. You know, the electrons will go visit hydrogen, but they don't really like his place. It's a little messy. They'd rather spend time with chlorine. Chlorine has lots of friends over. Better place to go. Hydrogen gets the pity visits. Now, if we were to draw another one right next to it, and we also have a positive end and a negative end, what will those two do to each other? Pardon?
Repel.
Where will they repel?
They will attract.
They will attract. If you take two magnets, they can repel, but the magnet will quickly flip and then attract. So I've drawn it so the positives and negatives are together, and you have this attraction. That attraction,
So where are those bonds?
the attraction.
So they're not actually like.
Well, I find it difficult to answer that question because none of this is really there. I mean, a bond is just electrons moving around. They're not really permanent. And fundamentally, according to string theory, everything's just forces wrapped together like strings. There's nothing real. And now you have to know that for the rest of your day. That's what we call a dipole-dipole bond. It's an electrostatic attraction between two molecules with dipoles. And I know my writing isn't the easiest. Are there any attraction? Looks a little weird. No, it's not strong. NA? Could you put away the computer? What are you doing? In your bag, please.
Can you stop that?
That's okay. Leave Andrew alone. No. This attraction between two things with dipoles affects a lot of things. A lot of organic things have dipoles. Sugar does. There's a lot of OH bonded around it, so it forms a crystal, solid at room temperature. The paper that you're writing on, except, go isn't. What are you doing?
I was just checking.
Put the laptop away. No, you don't even know it's for lunch. You'll know when you go there. They don't change it if you don't like it. I don't know if you've noticed that.
Yeah.
Pardon?
So mentally prepared.
It's to be mental. An idea has been formulating in my brain over the past number of months. Because I've always said, you know, if you're abusing your thing, I tell you to put it away. If you do it, if there's a lot going on, I start taking them. But what if I just had like a cell phone blanket? Like that we have in the houses. And then as soon as you walk in, you have to put it in the blanket.
That sounds like a bad idea.
No,
And then you wouldn't be distracted.
No, that would be more of a distraction because it's so like glorious.
I'd put it behind the flag.
The flag is also very glorious.
It is its own distraction.
You don't need a blanket. Just
Okay.
let people to put their phone to the test.
Now my question's distracting you. Bonding force. The bonding force between molecules with permanent dipoles. Oh, right. I was saying your paper is held together with this. Wood fiber has a lot of polar molecules in it. And so when those individual strands are next to each other and they're dry, they stick together and form paper. So your paper is not held together by covalent bonds or ionic bonds, other than the actual wood fibers themselves. But the wood fibers stick to other wood fibers purely by dipole-dipole bonding, which is why if you put it in water, which is a very strong polar solvent, your paper eventually just sort of dissolves away because water will disrupt all of that process. A lot of your hair, once it's dry, is held together in a particular shape by dipole-dipole bonding. So if you wet your hair and then you let it dry, it'll kind of keep that shape because it will form new dipole-dipole bondings in that shape. If you have your hair done so that it's permanent, they actually break sulfide bonds in your hair and reattach them. Those are permanent covalent bonds, which is why they work. Also, the process of breaking them and reattaching them damages your hair each time, which is why if you do it often enough, your hair falls out. Two blankets, one with cell phones and one with really big pockets for laptops.
I think that's also a very bad idea.
I think the laptop one is better.
The laptop one is better.
Yeah, but it has to be like really big. I could take up an entire wall.
No, we don't.
I have entire walls.
No, we really don't need it.
I have so much room.
We need those ones.
Or we should
We do need the whiteboards, but there's like just a flag hanging there. Back of the door there. Back of the door there. Above the couch. Anyway. Hydrogen bond. I don't know why there's a blank space there. We're going to there. How many of you are in biology 11 AP? You've done hydrogen bonding?
Yes.
Yeah, beginning. It'll be a review from beginning of the year. Yeah.
Mr. Duvall, I have a question.
Possessive statement. Do you sure you want to give it to me by asking it?
Yeah.
Okay, go.
What are your thoughts of having porta potties in the room? Like
Porta potties where?
in each classroom.
Oh God, that would stink. That's worse than the fish. That also means that someone would be using it in the classroom.
That's more effective, actually.
Yeah, all the farting would happen right here.
But like you'd be able to listen to your lectures while you're in the
No,
bathroom.
but you'll be able to listen to the one who said that.
I do recall the tale. I'm going to keep writing while I'm doing this, so you can keep writing. Of a professor who he told this. A show has come out based on his teaching life, and he worked for an inner city school in London. Very rough school, but they had a very good deaf program. And the night before, he drank a lot of root beer, let's say, and then feeling hungry, had a very hot curry afterwards. So the next morning, teaching class, this school had a very good deaf program, as I said. He feels a little worse for the wear. He'd also been living with his mother, and she had done his laundry for him because, you know, he was only 33. So he feels this coming on. He leaves the classroom to go to the washroom, and it is unbelievably loud. He basically does a Jackson Pollock on the toilet. It's a type of splatter artist. And he's just like, oh God, I can't believe this is happening. Oh God. And then he notices that the underwear he has on, his laundry had gotten mixed up with his mom's laundry because she did it. He's wearing his mom's underwear. And then he's just feeling like the low post part of his life. Like, oh my goodness, why is this happening to me? I've never been this sad. I am worthless. He's saying all this to himself in the bathroom. Anyway, he takes like 20 minutes, cleans himself up, muttering to himself. He goes back to the classroom. There's about 5 students there just like this. Because, of course, it's a school for the deaf, and he was hooked up to a mic the entire time. So when you said people going to the bathroom in here, that's all I can think of. I don't want to hear any of that.
There's gonna be it's gonna be soundproof.
That's just a bathroom.
It's soundproof.
If it's soundproof, your reason for having it so you can still hear me is no. You could just take the live stream with you.
Sure, but the Wi-Fi doesn't work.
There's already a sink in here. So.
It's already a sink in here. That is not. No. I don't know what you're planning, but no.
We just put a little.
Okay. I am going to discuss the hydrogen bond is just a dipole-dipole bond, but it occurs when hydrogen is bonded with our most electronegative elements. So it's a very, very strong dipole-dipole bond. It only occurs when hydrogen is covalently bonded with either nitrogen, oxygen, and fluorine. So it is just a dipole-dipole bond. You will see it, for example, water bonded H2O, H with oxygen. If we're looking on other planets for oceans that could support life, we look for water because of this strong dipole-dipole bonding. It has a large range between where it is solid and a gas, and that allows life chemistry to occur. Chemistry takes place very quickly in a liquid solution, and so you kind of need that for life. You're not going to get much in a solid. Gases don't have any solid structures, and so water seems to be the best way for the chemistry of life to occur. So we look for water, but we also look at ammonia. Ammonia Cs would have very similar properties to water because they also have the dipole-dipole bonding. Possibly a hydrofluoric acid C, but that'd be a weird world, and also that's incredibly reactive. Probably rip apart anything that started to form. And you'll see OH bonds on other molecules. They would also have this type of bonding. So, for example, if you were in Biology 12 and I asked you to draw, or Biology 11 AP, a hydrogen bond, I will show you the most common mistake and where the hydrogen bond actually is. Well, I'm going to actually ask you for that. Who's making it? Stop slurping. Which end's the negative end? Oxygen. Oxygen will be negative, and any molecule you have, the hydrogen is the most electropositive thing we have that can still be covalently attached. So the hydrogens are generally always going to be electropositive. Where's the hydrogen bond? And because I want to be specific, I will number them. Where is the hydrogen bond? So if you refer to an H and an O, just tell me which ones.
H1 and O2.
H1 and O2. So this, oops, I started drawing in the wrong spot. H1 and O2. This, right there, I'll draw it in dots because it's not a full bond. There is our hydrogen bond. It's a dipole-dipole force. Between molecules. The most common error that a biology student would make is that they often point to this bond, the covalent bond between them. That's not a hydrogen bond. That is a bond to hydrogen, sure, but the hydrogen-hydrogen bonds are the ones between different molecules. And that's what gives water its unique properties. Of course, really important if you're studying biology, because that's what gives water surface tension. So it allows insects to sit on top of the water. Because when water's at the surface, those bonds can't point up. They point to each other, and they form that skim. So now insects can land on water. When water cools down, the ice, those hydrogen-hydrogen bonds have to line up. And so when they line up, they actually make ice a little less dense than liquid water, which means that ice floats on top. That provides an insulating layer over the coldness of an Earth winter, which allows life to continue in the pond below, and it doesn't completely freeze solid. Water has a lot of heat retentive properties. Right now, it's getting warm. If you were inland, let's say in inner BC somewhere, Kelowna, how much hotter does it get than around here? A lot hotter. And that's because we have a whole ocean. All those bonds between water molecules, when it heats up, they have to break. And then the water evaporates. That takes energy, and that sucks away the heat from the environment. And so you'll find that in coastal areas, the weather's always milder. In the summertime, you break those bonds, that sucks in the heat. In the winter, those bonds reform, and that releases heat. The process of freezing is exothermic. You have to take heat away from it. And so our winters are also milder. And so it regulates the temperature. Your body uses it to regulate your own temperature. It dumps heat into the water, which circulates around your system, and then you radiate heat if you're too hot. If you're really hot, what do? You've been really hot lately?
Yeah.
What does your body do when you're hot?
Sweat.
You sweat. If you want to cool down, don't wipe the sweat away. The purpose of the sweat is for it to evaporate. When it evaporates off of your head, your arms, that process is endothermic. It sucks the heat away, and as it evaporates, it cools you down. So it may feel uncomfortable to have the sweat there, but it's acting as a purpose. When you just take it away, you actually haven't cooled yourself down. By it evaporating, it's using these properties of waters. That hydrogen bond to break it requires a lot of energy. That energy then gets put into it, into the evaporation, and then that cools you down. Dogs can't sweat, so that's why you'll see them panting in the heat. They have to evaporate the water right off their tongues. And so they're like, if you are very warm, that can also work for you. You're also a lot bigger than some dogs, and so it doesn't work quite as well. But there is, I think, a couple breeds of dogs that sweat. I have to double check, but most of them have lost that ability. And they just have to evaporate off their tongue. Okay. We've done it through here. If we have a sugar molecule, sugar looks kind of like this. And I think this one will have like a CH2, CH3 or something, and then that will have an OH and an OH and an OH and an OH and an OH. And so all of these are potentials. All of those have a dipole. It's asymmetrical. So there's a ton of opportunities for it to bond with something else with dipoles. So this is why sugar can dissolve in water. Water is also highly polar. This is highly polar. They can interact with their positive charges. Sugar is a crystal because these dipole-dipole forces are strong enough for their hydrogen bonds to make it solid at room temperature. No, Andrew.
What?
No. And I don't want to have to ask you again for that. London forces, or van der Waals forces. I will explain van der Waals because they use these confusingly in chemistry. It's just because it's used for two different terms. Van der Waals forces is the electrostatic, and despite my love of saying it, the best term to use is London forces. It is more precise. The electrostatic attraction between molecules with temporary dipoles. Back here, these are permanent. This is always, we didn't put the sign in there. This is always negative, that is always positive. So these are permanent dipoles. London forces are about temporary dipoles. This occurs everywhere, all at once, like the force. And it is a very, very weak force. So let's demo this. We're going to need, I will ignore, if we could take these desks, move them a little to the side. We're going to do the center of the room, so shove these forward. And we get the four of you, and how about three of you, and here, one over. Going red? Okay, come on over. But no, like up out of the desk, everybody. We need to clear some space. Move your desks back. This is a full body demo. Yeah, just move your desks around. We're gonna move them back in a second, but we need the room.
You know what I heard? This is Moses parting the Red Sea.
you are the protons in the nucleus of a helium atom, which luckily means you don't really have to do it. You just stand there being attractive to your 2 electrons. Well done. You two, when I say go, you're going to just walk around. You're in your orbital, so you're just going to go around the nucleus. Okay. So, where are here? We're going to use this area, so let's go in here. If you guys can stand back. So standing there, come a little closer this way. There we go. There, your protons in the nucleus. You're just staying there, being attractive to your 2 electrons. You're already an electron. Come on in there. You guys are electrons, so you have to wander around in your orbitals. So if I can get the electrons to wander around in their orbitals right now, right? Okay. Just move as the spirit moves you. No hitting. Walk at your own speed. Stop. You don't listen to instructions very well. However, this will kind of work because right now, where are the electrons?
They're behind.
They're behind, right here. So here, if I was to cut this like this, or right through the middle, we've got a negative side and a positive side. And here it kind of is, just by chance, if I cut it right through here, I've got a positive side and a negative side. Now, in terms of their orientation, I'm going to just pretend that the whole thing flipped. And so, no, actually this works, because your positive side there, the negative side is here. They would be momentarily attracted to each other. It'd be like a little fleeting glimpse, because the electrons are on just the right side to have a negative side over there and a positive side here. We have a negative side over there, which is now attracting that positive side, and a negative side here. But as soon as I say walk, it goes away. Stop. These electrons, right, once again, we've got a positive side and a negative side. If this happened to be in the right configuration, so I'm going to move you right there just for a second, then we would have a negative side again. It would be a momentary attraction. Does this last very long? No. This would be very weak. How could we make this force stronger?
Yeah, add another one.
Add another one. Add more electrons.
Yeah.
So for this force, the bigger the atom, the stronger this force is. So it's weakest in hydrogen. It's only got 2 electrons. So we can look at F2, which is symmetrical. It is only using this type of force, which is London forces. It's a gas. It doesn't hold together very well. Chlorine, still a gas, doesn't hold together. Bromine's a liquid, and it only has this force. But bromine has 1, 2, 3 layers of electrons all moving around. So there's a slight chance that some of them will be on more on one side than the other. Every electron or bond you add is another sort of ticket in that lottery of whether or not they'll be there. Iodine has so many electrons, the force is large enough to make it a solid at room temperature. So they have to be very large in some kind of way. Thank you. Put the desk back. Give yourself a hand. Well done.
Good job.
While you're doing that, I'm going to cheat and keep drawing.
Dad, let me see your polo. Let's get the full body then.
This guy shows the design. Yo, I just found a new layout.
Gentlemen, what are you doing? Focusing back.
We're discussing about the electrons.
Andrew?
No, I'm not speaking. One moment.
If the electrons happen to be more on one side than the other, then we have for that brief moment a temporary negative side and a temporary positive side. And we'll get a very fleeting temporary dipole. Anything with electrons has this force. If you have a permanent dipole, that is just so much larger and so much more important than this. You don't really consider this unless it doesn't have that. So this is a temporary dipole. It's a bit like a personality. If you are permanently attractive, you're just attractive. You don't need a personality. But if you're not attractive, then you need a personality, and we consider that force.
Wait, so what makes it temporary?
What's going to happen the next second to those electrons? Ryan, what are you doing?
You're distracting me.
Yeah, turn around in your desk. Do I need to move you?
I think you should.
I think that would help me.
Because you could move right there. I think that might be good. Anyway, Nicholas, what would happen to these electrons in the next second? Yeah. So in the next second, I mean, this electron could be over there, and that electron could be over here, and now it's basically even again. It's only when they happen to be more on one side than the other.
But isn't that the same with the dipole? Like,
In the dipole,
dipole.
whoops. In the dipole, these electrons are pulled over because of oxygen's electronegativity. They are permanently more on one side than the other. So this charge separation is permanent. The electrons aren't going to randomly go to this side. They're more attractive to the oxygen. Whereas here, because there's no other electronegativity here, they just happen to be on one side. That's going to change in the very next second. Or femtosecond, to be honest. Yes?
What did a dipole mean again?
A separation of charge.
Separation of charge.
So one end's more positive than the other. This is a temporary dipole because we have a separation of charge. The negative electrons are on this side. The lack of electrons mean we're seeing the positive from the nucleus. And so we have this temporary dipole. This is fleeting. It's going to end right away.
So those dots are the dots.
Are the temporary dipole.
So what's a, oh, wait, there's a permanent dipole.
In the last one we did.
So what if you drew it like how you draw the H2Os like this?
Yep.
How does the temporary dipole work like that?
So if I was to do it like, let me finish off this one, then I'll draw one like that. Okay. One thing, as we said, because they are dependent on the number of electrons, and the more electrons you have, the more chance that you have happening. They are larger for larger molecules. So the larger the molecular atom is, the more chance, the stronger the London force. So if I was to show that, let me give myself a little bit of room. So if an example of that could be, let's do methane. Methane is CH4. So we got H, 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 H. Every one of these bonds has a potential for the electrons to be more on one side than the other. And so if I was to draw another one next to it, I'm going to erase this in a second, so don't draw the second one. I would just say that by chance, the way these electrons move around, this side happened to be negative, this side happened to be positive, this side happened to be positive, and this side happened to be negative, and we got a dipole-dipole bond. But in the very next second, it could be even because it's symmetrical and it would all go away. There is no area that's always positive. Okay? Now, if I was to compare two molecules, like methane,
Just like to determine if something, the difference between something is negative or positive, it's just the difference if one of them is less electronegative than the other.
yep, and whether or not it's symmetrical.
Okay.
So methane is perfectly symmetrical. I've drawn it two-dimensionally as symmetrical. Three-dimensionally, methane looks something like this. The bond goes away, this bond comes towards you, and it forms a tetrahedron with every one of these angles at 109.5 degrees. And so it is perfectly three-dimensionally symmetrical.
Do we have to remember the line things with the coming out at you and the going?
I keep introducing them because we are going to use them in organic chemistry.
Okay.
Yeah, so eventually, yeah. Now, this has a certain potential for a temporary dipole. It's low, so methane tends to be a gas at room temperature. But if I do, say, methane, propane, what do you put in a lighter? Butane. Butane looks like this. There are so many more electrons in those bonds. Larger, therefore more London force. Therefore, it's a liquid. Small London force.
How'd you determine it was a liquid?
Because I've bought it. Like butane for your lighter. It evaporates quickly, but you can buy it as a liquid. It doesn't take very much to keep it as a liquid. Methane, you have to put under a lot of pressure to keep it as a liquid. Methane isn't bonded to itself very well. Now, if I was to say, let's keep that going, this one, it's a liquid, but it easily evaporates. What is something that is made out of long strings of carbons that's a solid or a like obvious liquid at room temperature? We burn them to provide energy. We used to set them on fire to provide light. Coal is one. We don't want to go into the structure of coal. That has a lot of different things. Basically, carbonized wood. Pardon?
Is it a liquid?
Can be, yeah.
Fossil fuels.
Fossil fuels. They're just long strings of carbon. If you have a wax, your structure looks like this. H, C, H, H, and then you go C, C, and then I want you to keep going about, I don't know, 60 times. So I'll just go like this, C, H, H, and let's just put a 40 there. C, H, H, C, H, H, H. This is very large. So it's a solid at room temperature and pressure. This would essentially be a wax. The lipids that make up the membranes in your skin, I think they're about 26, 25 carbons long. So they're basically solids. If you ever had skin is sort of a loose solid. We have some problems. We actually have to introduce bends into those molecules so the London forces get disrupted. That's what the purpose of cholesterol is. Cholesterol is in animals to disrupt the London forces between your membranes in your cells. Otherwise, it wouldn't be liquidy. It would have the consistency of butter, which means that you could take your face, you could go like this, and it would stay that way because there would be no fluidity to your membranes. Cholesterol's in animal products because animals have to run around a lot, and so those fats have to be a little bit more supple. And so they throw in some cholesterols in between the membrane to actually disrupt that process. To go into a little bit more into that, depending on how much biochemistry we end up doing. Is there anyone other than Jillian who's in Biology 11 AP? The only one? Do you do trans and cis bonding?
We did at the very beginning because we did this whole thing with like fats and like
Fast
trans
and-
fat chains.
yeah,
We talked
yeah.
about like cis fats, trans fats.
Yeah.
Is that AP stuff?
That's AP stuff. It's actually Biology 12 stuff. There is no such thing as a grade 11 AP. All AP courses are grade 12 courses. That's where you get the credit. However, Brentwood spreads it out over 2 years, so they do a lot of the grade 12 stuff in the grade 11 year, so that you can have more time for the AP stuff.
I've done that before.
Pardon?
I've done that before.
Yeah, and in a different school, they will do things at different rates. Okay. Very large. Lots of electrons. And chances for temporary dipoles. Which we are going to call London forces. Okay, good. Anybody still getting this done? We are going to be just screaming through the notes, just to keep you a heads up, because of the way they canceled classes for regatta, where we lost a couple that other classes didn't. So, yeah,
I have a question. What's our like final exam?
it's Mr. Snow and I are writing it right now. It's going to cover the topics of the year. We'll get you some review sheets, but if you just went through and our Hebden sheet, we did all of those, you'd be fine. It's just all of those topics. Pardon?
Isn't he an AP Chem teacher?
Yeah, but his students write the same exam. We don't put AP material on it. Although sometimes we'll have a last section that will say, do 2 of the following 5 questions, or 1 of the following 3 questions, or something like that. And then he could put an AP question there that his students could do if they wanted to.
Oh, but it's only for his.
It's to see where because if you have a grade 11 AP, he needs to know what their grade 11 mark would be.
Oh.
Right? So for them, they've done things a lot faster. Often they do really well on it, or they don't. The difference between Chemistry 11 and Chemistry 11 AP is just the amount of stuff you do. The stuff in AP is not cognitively harder. You just do it faster.
Can we have our finals starting from like our previous test? 'Cause, like,
Oh no, the final covers the whole year. It on the last week before you go. Yeah. Tatum, did you have another question?
So just kind of 2 questions are there. So there's going to be like multiple choice and like random question.
Yeah.
Like that's kind of 2 seconds.
Yeah. Well, we haven't written the test yet, so I can't answer detailed questions.
Yeah.
Yet.
And also, do you know when the exam schedule is going to be released for the last week?
No. Ms. Merlin will do that. Okay, next page. This is just a summary of all the different strengths of the bonds we've been discussing. Can you put that away in your? Take your Apple Watch off and put it away, maybe. I'm going to also summarize what a van der Waals versus a London force is. There are some chemists, and you will read textbooks and online, that will refer to all of these, from the hydrogen bond to the dipole to the London forces, as van der Waals. So it means everything. And then there are some chemists that will just use it to mean London forces. So it is important to look at the context. If you're studying online, you're getting your information from somewhere else, or you're looking something up, depends on the chemist you're talking to and where they were trained, which way they use it. I was taught that it was the same as London forces, especially here in Canada and a lot of the U.S. But if you're from Europe, they tend to use it to mean all of these forces, and it's just a difference linguistically. So be aware of that when you're looking up. The resources online can vary quite a bit, which is why it's more precise. Just use London forces when you mean this, and only van der Waals when you want to sound cool. Now, covalent is due to what? What's holding that together? It's a non-metal, but what's the force holding it together? Why are they? It's not their electronegativity. They're both electronegative. That adds to it. It is a kind of electrostatic. What's attracted to what? If you have a covalent, like if you have hydrogen and you have chlorine, what is causing that hydrogen to stick around? What about those electrons? They are bonded? Whose electrons are they? Oh, so they're shared electrons. But why is it attracted to those shared electrons? What is it about hydrogen that is attracted to those shared electrons?
It has another electron related to it.
Hydrogen actually doesn't have another electron.
Or it has, but it can be able to share one to like make the bond more like, let me see,
Stable.
complete, stable, yeah.
It does that to make it stable. But what part of the hydrogen atom is attracted to those electrons? Yes? The protons. So it is always the protons attracted to the shared electrons. So it doesn't go beyond that. It is self-contained. And so covalent compounds, unless they have a hydrogen bond, a dipole-dipole, or a London force, don't interact with each other very well. Whereas ionic, it is all forces between all of the atoms. So these are all what we call intermolecular forces. And these, which are in the thing itself, are intramolecular. Intra meaning inside molecule. Inter meaning between or outside molecule. The internet, internet, is a communication between computers over the entire world. Intranet is communication between the computers on the same local network. So when you connect here in the school to school things, you're using the intranet. When you connect to the outside world, you're using internet. Just if that helps you learn the terminology. For these, dipole-dipole and hydrogen bonding, and I'm going to color code it because I'm overwriting things, must have molecular polarity. And what are the two things that you need to have for molecular polarity? Asymmetry and a polar bond. Any questions then about the relationship of any of these forces? What distinguishes between the hydrogen bond and a dipole-dipole bond?
Members with each covalently bonded to NO and F.
H, N, H, O, and H, F is only the hydrogen bond. Excellent. And if these are shared electrons, this is a full electron transfer. For ionic, it is just electrostatic attraction. So a little overall summing, and then this shows the strength. The weakest of all bonding is London forces.
What's James?
The strongest of all the bonds.
How are we gonna learn that?
You haven't seen his movies? Anybody still need that up?
Yeah.
What does the green rating under ionic say? It says full E.
Full electron transfer. Kirk has James Bond as one of his middle names. So in the future, if he ever wants a passport that says James Bond, he can do that. It is apparently only $75 to change your name. So, anybody still ready? Okay. Large molecule. Oh, I already drew a little bit of this, but let's do the two examples. We'll start off with C26, H54. One, two, three, bracket, C, H, H, bracket, 1, 2, 3, just to give us the sense of size. And it's good practice for drawing organic molecules. Because you'll get sick of drawing them this way, and then I'll show you the easier way later. This is a solid at room temperature and pressure. This is essentially candle wax. Non-polar. And because there's lots of bonds, there are a lot of individual areas where we could say, oh, this is now slightly negative and this is now slightly positive, and maybe this area is an area that's slightly negative and this area is slightly positive. There's a lot of places for this to occur. And if there is another one lined up alongside of it, Then there could be a moment, well, that's negative. We could have a slightly positive one there with a slightly negative here, slightly positive there, slightly negative there, and then we have another opportunity for a temporary dipole-dipole bond. So this is the London force.
Bless you. Bless you. Bless you.
I got very good at not sneezing over the pandemic. Standing in the middle of a grocery store, you sneeze, everybody looks at you, you get tackled.
Machine with the lava question.
Yep.
So, for the C, for the carbon 26 and hydrogen 54, is that what it is?
Yep.
How do you know how many C's and H's there are?
How did I know?
Yeah.
I doubled it and added 2. Every carbon has 2 hydrogens,
Yeah.
except for the ends where they have an extra one each. So if you want to, for a straight molecule, the formula is CnH2n plus 2. So if this is 26, 26 times 2 is 52,
Yeah.
plus 2, 54.
So why can't that be dipole-dipole instead of temporary?
So how do you know how many?
Because in the next second, this is not a permanent dipole. So in the very next second, this could move, this could go away. It could move somewhere else. It's not going to be there because there is no permanence to this. That was just because the electrons happen to be arranged. Like when we did the example, they were just wandering around. And the next minute, they're going to continue wandering around. And so it's going to disappear. So it's just based on chance. Yep.
How do you know how many H's and C's is going to be in that category?
How did I know how many C's?
Like in the, what is that called?
Oh, sorry, I didn't put a thing with my bracket. This is supposed to be 26. I've got 6 there, so this should be 20. Sorry, repeat this middle part 20 times.
Oh,
That's why I put the bracket. I didn't want to have to draw 26 carbons.
and
You can if you want, though.
there's only 6 bonds or 6 electrons in the middle.
What do you mean there's only 6 electrons?
H, C, H. And then there's like another dash inside. Like inside the parentheses.
Oh, it doesn't matter where you put the dashes.
Oh,
You know that this carbon is connected to the next carbon, next carbon, next carbon, next carbon by individual single bonds.
it doesn't matter how many there's supposed to be in that diagram. Like there's like there's like 16 H's and there's 7 carbons.
There is 26 carbons.
Is that only?
This bracket is repeated 20 times.
Wouldn't that make 27?
20, 21, 22, 23, 24, 25, 26.
Oh, I'm bad at math. Yeah.
And the more bonds you have, the more chances. This could go away, as I said, but it could also reappear. Because you have so many bonds, it could reappear at a different spot.
How does it just go away?
Pardon?
How does it just go away?
What are the electrons doing? Yeah, so it's due to electron movement. And the electrons are always moving.
Like around the H? Or
In the bond.
oh, in the bond. Okay.
Yeah. So most of the time, it's going to be even. But there could be a high concentration, just for a fraction of a second, over at the hydrogen and a low concentration over at the carbon. An unequal amount across those bonds. And the more bonds you have, the more chances you have of that occurring. Or just the more electrons for like a bigger atom with more shells. Good? Good. Okay. Small molecule, small London forces. I won't draw it out twice, but I'll give you a small molecule. How many people know what this is? It's a very good summer molecule. 3 carbons, 8 hydrogens. C3H8. Does anybody know what that is? It's a gas at RTP. It is non-polar, so unlike the previous one, it is not a solid. Low chance of London forces, because we've only had this limited area for them to appear, and we don't have the whole chain anymore. We just got 3 carbons. So it's very short, and we use it in summer parties. Yeah?
Propane?
It's propane. Propane and propane accessories. Or, as someone said, do you mean a gas grill, Mr. Neufeld? I don't know what country you're in that you don't refer to propane as propane, but... Or maybe they just always use charcoal. Even though that's icky.
For London's force, you said like electrons are moving around, but aren't electrons like exist everywhere?
Yes.
Why it's like
Well, they don't exist everywhere in unlimited amounts. This molecule, this molecule has more electrons. Like you could count them. 2, 4, 6, 8, 10, 12, 14, 16, 18. 18 plus 20 times 6 plus, like that's a lot. Whereas this one only has 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons done. The amount of electrons something has is dependent on its orbitals and the amount of bonds it has. Okay. So it's a very different. Another way of showing it would be, I'm going to show 2 molecules here, and we're going to draw them correctly. So carbon to hydrogen to hydrogen. You would draw, this is coming out at you 3-dimensionally on the page. So the small end of the triangle is at the carbon, and the big end is out here because it's coming out at you. Hydrogen. And the big end is here because it's closest to you, and then it goes away. That is the attempt at drawing. This is how we draw a 3-dimensional object on a 2-dimensional page in biochemistry. We use these types of bonds with the dashes and the bolding to show which direction, if they're coming into or out of the page. Every one of these angles between each other is 109 degrees, 109.5 degrees, and so this is a perfectly symmetrical molecule, but it is very small. This is methane, and it is methane gas. Versus, we could draw the exact same molecule, but instead of connecting it to hydrogen, connect it to chlorine. Oops. Hydrogen. Oops. Not hydrogen. I said chlorine and chlorine.
Which symbol means behind and in front?
Take a guess. Which one?
I'm gonna say the in front is like the all black like triangle.
Yep. Because it's coming out at you. So chlorine has all of these extra electrons that hydrogen doesn't have. It's physically bigger with more shells. So we've got the first shell, the second shell, and then you see that third shell that it's covalently bonded to. So there's a ton more electrons on here. This is a much bigger atom. This atom is big. This is carbon tetrachloride, and it is a liquid. at room temperature and pressure, and there is no difference between these in terms of their bonding, bond angles, how they're connected together. These are otherwise identical molecules. But because the chlorine is big and has more London forces, it can be a liquid. This is the stuff that in my second year of university, they took away from us because we had them on the lab desks. It's really great for dissolving non-polar things because it itself is non-polar. But a group of us started spraying it on each other's pants because polyester pants would dissolve under carbon tetrachloride, and we thought that was hilarious. It's also a class 1 carcinogen, which we knew but did not care that much about because we were silly. We were the reasons you can no longer have nice things at the University of Victoria. Yes?
How would you show a double bond if you were doing like 3D representation?
Oh, the 3D represent. You often wouldn't. Because you would just go like this if it was flat, right? If you're doing it like this, you're often just showing connections and you just say that's a double bond pointed this way, and you draw it exactly the same way. When we tend to draw a more complex structure, the double bonds, because of the nature of when you form a double bond, it flattens the molecule because it takes one of those poles out. So we usually draw it with the double bonds being flat and then everything else poking away from that is the easiest way to do it. Because when you said that, I'm like, I've never done that. And I realized why. It's because I just draw the double bonds as flat. Yeah. Good question. Any questions? Excellent. As I said, we're behind, but we're getting caught up so well. You get another handout. 3, 4.
It's 106. Did we leave?
No, you're going to learn more chemistry, even if it kills you. Some of you may die, but that is a sacrifice I am willing to make.
I'd say Ryan goes first.
You've seen that scene from Shrek?
There's only two.
When the little king is talking?
There's only two.
No.
The little tiny king.
Okay.
Yeah, of course not. When he sends the knights out, he goes, some of you may die. That's a sacrifice I will make. I've always liked that phrase. Put away phone.
That's one put away.
The little tiny king guy.
And then I was helping down with I was
Nice. Okay. Now that we know about the forces, we're going to do why things dissolve. The golden law. The golden law for dissolving and solvents and solutes is like oh God, I can't spell dissolves. Dissolves like. And under this definition, polar and ionic, because they're both permanent positives and negatives, are considered like, as opposed to the non-polar things. So polar and ionic solutes dissolve in polar solvents. Theoretically, they would also dissolve in an ionic solvent, but an ionic solvent would be 2,000 degrees Celsius and probably burn up most of what you're trying to dissolve in it. So I'm not going to worry about ionic. I don't know of any ionic solutions that are at room temperature. Non-polar solutes dissolve in non-polar solvents. So if you have salt, which is ionic, it will dissolve in water, which is polar. If you have sugar, which is polar, it will dissolve in water because it's also polar. But if you have fat, let's say some oil, then you need to take that. You have like a really bad oil stain on your clothing. Where do you take that to?
The laundry.
You do take it to laundry.
Oh, you-
But if you have a bad, often where people take it to, you don't actually often just use the washing machine at that point.
Don't you just
It's
use
a stubborn oil
solvent?
stain that won't come out.
Don't you use oil solvent?
Yeah, who does that?
No one.
Dry cleaners.
Oh.
The reason dry cleaners work so well is they have a ton of non-polar solvents that they can use to get all that oil and dirt off of your clothes that you can't use at home. It's also why in Breaking Bad they make a great front for making methamphetamine because they use a lot of solvent and chemicals in their process.
They just like bleach things to make the like.
Bleaching isn't cleaning, it's just taking the dirt and making it white.
Oh.
That sounds a lot like colonization. That's bad.
I did not see
That phrasing was wrong. Bleaching. What bleaching does is it takes the molecules that are there, like whatever's a dye or whatever, and it often will either oxidize it or chlorinate it, depending on the type of bleach. Bleach used to be only chlorinated, and it rips it apart so that it no longer has any color because it's not the same molecule anymore. So it's damaged, but it makes you don't see the stain anymore. It doesn't actually remove the stain. It just makes it so it doesn't have a color. Ironically, over time, bleaching will yellow your white and light clothing, which is why some people will add a bluing agent to counteract that. Okay, I just used a bunch of definitions. What is a solute and what is a solvent?
Solute is the thing that dissolves in the solvent.
A solute is the thing that dissolves in the solvent. Sure, Nick?
Is it the solute or solvent?
Yeah, which one's which?
Solvent is like particles that dissolve in the solute.
No. Solvent is the one that dissolves the stuff, and solid is the one that gets dissolved.
Solvent is the one that does the dissolving. Whereas the solute is dissolved. And I define it on the very next page. So now we haven't done a solution. What's a solution?
It's like a mixture of.
Very special. We did at the very beginning of the year, we did types of matter. What type of mixture is it?
Homogeneous.
Homogeneous. You can tell if someone's Canadian, a UK, someone from the UK, or American, depending on how they what they refer to as milk that hasn't been reduced in its amount of fat. So if you're from the UK, you buy full fat milk. When you're in the US, you buy whole milk. But if you're in Canada, you go in and you buy homo milk.
Wait.
That one question will separate which country you came from.
So you're right, it's G-N-O.
Homogeneous milk.
Like no fat.
Oh, yes, right?
So,
Did I spell homogeneous correctly?
Isn't it?
yeah.
Are you sure there's an E after the N?
I think so, but I'll double check. It's like the word banana. Sometimes I don't know when to stop spelling it, and it just becomes banana na 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 na.
No, but there's not an E after the N.
No?
Yeah, it's N-O-U-S.
Well, let's see. Oh yeah. Homogeneous.
What? No.
Yes, homogeneous. Definition and meaning, Merriam-Webster. Homogeneous, homogeneity, heterogeneity, homogeneous. Word up.
No, look.
Yes, look.
Yeah, look. Look closer.
Oh,
Yeah.
I look. The one
Oh.
that I looked up is a biology something.
Oh, that's a different word.
Oh yeah.
Solvent
Oh, it's a homologous one.
does the dissolving. And I need you to have these definitions before you leave. Part in greater amount, because sometimes there's two liquids, so we will put that in. Solute is dissolved. Part in lesser amount. Once you have those terms down, you are good to go. That was a lot of notes today.